correlation. We are going to quantify correlations. And like always, I keep referring to this section as something weird, 4.1 or 4.2. Just ignore that. That's from a different book. Okay, enjoy. Correlations.
Hey folks, chapter 4.1 and 4.2, least squares regression and scatter diagrams and correlation. Okay, so I made a little graph, daughter's height, mother's height. So we have the x variable as mom's height. Hey folks, quick little interruption. Someone just pointed out to me that my 15-minute video had a mistake. In the next 15 minutes, you're going to see a graph, and I call the x, I call it daughter's height. It should say mother's height. And then over here on the y coordinate, it says mother's height. It should say daughter's height. So this is what it's supposed to look like. I will fix the video in the next day or two, but apologies. So as you watch the rest of this video, just know that all the math is totally good. This is supposed to be mother's height on the x. This is supposed to be daughter's height on the y. Ugh, okay, sorry about that. Keep watching. The y variable is daughter's height. So let's see, we have the x and the y. This is mom's height. This is daughter's height. Okay. Now the x is sometimes called the explanatory variable. Explanatory variable. And so if that's the explanatory variable, this would be the response variable. Or they sometimes use the words independent and dependent. So the daughter's height. So here's how I'm thinking about things right now. Oftentimes you can argue about which one is x and which one's y, like which one explains the other. But to me, the way I set it up is the mom's height explains the daughter's height. So the mom's height would be the explanatory, and then the daughter's height is a response to the mom's height. Okay, so in terms of independent and dependent, the daughter's height depends on the mom's height. So this is the dependent variable. And if that's the dependent, then this is the independent. They like giving everything multiple names to confuse you. Okay, so the x and y, we could also call it the explanatory variable and the response variable. We could also call it the independent variable and the dependent variable. Okay, so they give us some data for mom's height and daughter's height. Let's make a scatter plot. Okay, so I'm just going to think of these like ordered pairs. So that first one is 63. The mom is 63 inches tall. The daughter is 62. So the ordered pair is 63, 62. Be able to see that? Let's see. Probably. Okay, so over 63 up 62. Put a dot. Next one, 65, 64. Over 65 up 64. Put a dot. Next one, over 61 up 62. Put a dot. 62, 63, 62, 63, put a dot. Remember, this is the x, and then the y would be mom's height. Okay, and then we have, 71, 70, 71, 70, that's way out here. And then we have 63, 64, 63, 64. Okay, so here's our scatter plot, all of these dots, and we're wondering if there's sort of a line that describes these things, a linear relationship. So imagine, if you will, that there's a line that sort of describes the data. Mathematically, if you've taken some calculus before, they call this the least squares regression line. Least squares regression line. Because you see how every dot is sort of above or below the line? So mathematically what they did was they took those distances, squared them, and then minimized it. And this is the line that minimizes these distance squared. So this line is called our least squares regression line. Some people just call it a regression line, or maybe once we find the y equals mx plus b for that line, we might call it the linear model or the model. Everything has multiple names. Super confusing. Okay, so first question was, what did they say? Draw a scatter plot. Okay, we drew a scatter plot. So that's just the dots. That was our scatter plot. Find the correlation. Okay. I'm going to show you how to do this on Excel also, but right now I'm going to use my calculator. I'm going to pretend that we can see things. Okay, so I'm going to enter the data as two lists. Stat, edit, enter. List L1, I already put the data in. L2, there's some wrong numbers, so let me go up, hit clear, hit enter. Now L2 is nice and clean. 62, enter. Again, I already put the mom site in before I started the video. 64, enter. 62, enter. 63, enter. 70, enter. 64, enter. Okay, now I'm going to use a stat test. Let's see, I go to stat. So once I have all my data in list L1 and L2, I go to stat, tests, and then way down there, there's a linear regression, linreg t-test, linreg t-test, linreg, linear regression, t-test. T because we're testing whether or not the correlation is statistically significant. Just go with it for a few, hit enter. It says the X list, okay, L1. So put L1, you might have to do second one. Mine already says L1 and L2, so that's good. And then just choose the does not equal sign. We're wondering if the correlation is or is not 0, so just choose the does not equal sign. Go down to calculate, hit enter. And remember, we're trying to find the y equals mx plus b from algebra. They call this the y equals a plus bx. And the a, it says, if you scroll down, it says a is 12.866. Y is equal to 12.866 plus, and the b, scroll down, it says 0.7994, 7995 plus 7995x. So up top here it says y equals a plus bx, and then it tells you down below what the a is and what the b is. Okay. What did they ask us to find? Oh, they asked us to find the correlation R. So the correlation R, what question is this? Find the correlation B. Okay, so question B, correlation, linear correlation, is represented by the letter R. And if you scroll down on your calculator, you're going to see 0.961411, blah, 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 blah. Okay. And then question C, it says, does a linear correlation exist between the variables? So how we get correlation R is just some crazy formula that you'll see in 4.1. Don't ever do it by hand. It takes forever, and it's super, you'll just make a tiny mistake. It takes forever. And just use technology. So you can always find a correlation. The question is the correlation good? Is this linear model that we created any good? So you'll notice we also have a p-value, a p. So if I scroll back up here, it says I have a p-value. It says p is equal to 0.0022. And remember, if our p-val is less than our alpha, then we would reject HO. That means something interesting is happening. So if p-val is less than alpha, then reject HO. That means something interesting is happening. Then yes, we do have a linear correlation. Yes, a linear correlation exists. So it's sort of, this p-value has sort of two uses. Is the correlation good? Like, you can always figure out a correlation. The question is there actually a linear relationship going on? So just make sure your p-val is less than 0.05. If it's less than 0.05, then say yes, a linear correlation exists. And it sort of applies to this y equals mx plus b, this least squares regression line that you make. Yes, you can just throw the numbers in and get a least squares regression line, but is it any good? So that's why we need to check our p-val. So yes, this least squares regression line is good. Okay. Hey, folks, turns out there's a C and a C2. Okay, well, why did I not just readjust the whole document with a C, D, E, F, G, H, etc., because I filmed everything first, and now I'm going back. So C2, pretend it makes sense. Okay, C2 is asking about R squared. R squared has a name because everything has a name. It's our coefficient of determination. Now, when you go on and take more stats classes, you're probably going to have to if you're a psychology major or sociology major. But what you're going to do is you're going to be making different models. And how you compare this model to that model is by comparing the R squareds. So right now, this is just a simple little model. And if you get a correlation R, then you can get an R squared. So we agreed that we had a correlation of R equals 0.9614. So the R squared would just be 0.9614 squared, enter. And so R squared is equal to 0.924 approximately. And then we usually talk about R squared in terms of a percentage. So we would say that R squared is 0.924, but when we ask about what it means, we would say 92.4% of the variation in the y, the daughter's height, our response variable in daughter's height, is explained by mother's height. So R squared is just the percentage of the variation in y that is explained by x. Okay, complicated if you try and break it down, but what it's generally used for is comparing models. So if you had another model with a higher R squared, then you'd use the other model. Okay, so if anyone asks, R squared, coefficient of determination, and it's the variation of the y explained by the x. Aha! And now it's going to ask us a bunch of questions. Let's see, new paper here. So we answered A, B, C. We're on to part D. Find the least squares regression line. Oh, we found that. That was y equals, I guess I could just put it right here. Here's part D. So here's part D. That was D. A was my scatter plot. So I guess I'm on to part E. E. If a mother is 64 inches tall, predict how tall the daughter will be. Okay, so that's where our least squares regression line comes in handy. Y is equal to 12.866 plus 7, or 0.7995x. So remember when we set things up in terms of x and y, x is mother's height and y is daughter's height. So the whole idea is you tell me how tall mom is and I will predict how tall daughter will be. Since we're predicting, if you look at our book, it's actually, they call it y hat. Most software packages just call it y equals mx plus b, but technically speaking, we're predicting. So our book will put a little hat above it. So you can put a hat over it if you want, since we're predicting. You tell me how tall mom is, I will predict how tall daughter will be. Okay, so mom is 64 inches tall. So the predicted daughter height, y hat, is 12.866 plus 0.7995. And then x, mother, we said is 64. Okay, throw that into my calculator. 0.7995 times 64, enter, plus 12.866, enter. So If mom is 64, daughter should be about 64.034. So nearly the same height. Okay, cool. So that's how we predict using our linear model. Part F says, calculate the residual for when a mother is 62 inches tall. And then it says the residual is observed minus predicted. Okay, so this was our predicted, right? Using this formula gave us the predicted. And the observed is the actual data, right? Mom was 63, daughter was 62. Mom was 65, daughter was 64. Okay, so when they say mom, so when mom is 62, we should have a data. If they're asking for the residual, then there has to be a piece of data where the mom is 62. And it turns out the daughter, if mom is 62, the daughter is 63. Okay. So this is our observation. Now so this is, mom is that one, right? 62. So let's use this formula and put 62 in it. So y hat, the predicted daughter height, is 12.866 plus 0.7995, and then mom's height is 62. And so y hat is equal to 0.7995 times 62, enter, plus 12.866, enter, 62.435. The residual is the observed minus the predicted. So the observed daughter height was 63 minus the predicted 62.435. And so that gives us a residual of 63 minus answer 0.565, positive 0.565. Let's see what that means. Over here, if we go back to our scatter plot, notice that we have our least squares regression line, and sometimes a data point is above the line. Sometimes it's below the line. If you're below the line, this blue thing right here, that's our residual. Positive residual, negative residual, negative residual. And we were looking at when mom was 62. Oh, that's this one right here, that location. Aha, positive residual. Kind of a small residual, just 0.565. Okay, making sense. Okay, cool. And then we are on to the next problem.